So we had a first stab earlier at trying to identify something that we could describe as the direction of a vector, and we realized that that was not the right way to do it because it was becoming very complicated very quickly. So we're going to do it in a different way, and in order to do that we're going to notice the following. If we use scalar multiplication and we apply it to a vector, we're changing its size, not its direction. Now, if so, for instance, if the scalar is greater than 1, we're going to make it longer, and if it's between 0 and 1, we're going to make it shorter. And if we're multiplying by a negative, we're not really changing the direction. The direction stays the same. It's the orientation that changes. That's what happens when we multiply by a number less than 0. Same direction, different orientation. Okay, so we're going to say that two vectors are parallel, that is, if they have the same direction, if and only if they're multiples of each other. So if two vectors are such that I can get one by multiplying the other by a scalar, I'm saying that the two vectors are going to be parallel, and I'm also going to say that they have the same direction. Okay. Related to that is the issue of how to use unit vectors. The unit vector of a geometric vector v of any geometric vector is given by this formula. Now notice what we're doing here. We're taking the vector v and we're multiplying by 1 over the length of v. Remember, the length of v is a number, and therefore so is 1 over the length of v. So I can also think of that as simply v divided by its length. So all I'm doing is I'm just shrinking it or making it longer, and I'm going to leave it to you as a little exercise to prove that any vector constructed in this way, as long as the original vector was not 0, was not 0, 0, so in other words, as long as it has a length, is going to be a unit vector. Okay. And we're going to use these unit vectors to identify the direction of a vector. So in other words, as the direction of a vector, we're going to say its direction is the unit, it's its unit vector. Okay, so that may look to you like a bit of a cop-out because I mean, we're not really saying much, but again, the efficiency and the effectiveness of taking this approach to the direction of a vector will become clearer as we start using these unit vectors and we start figuring out how we can extend their properties and generalize them. Now notice that if two vectors u and v have the same unit vector, that means that they have the same direction and the same orientation. On the other hand, if two vectors are such that their unit vectors are opposite, so one is equal to minus the other, so in other words all the components are opposite to each other, then that means that they have the same direction but different orientation. Let's finish this class with one important property of vectors and vector lengths that is important, but mostly from the theoretical point of view. Therefore, we're not really going to focus on it very much, but I do want you to take notice of it, mostly because traditionally it is a very important and commonly used property, but also because it's very easy to understand what it means. Okay, now, so the idea is the following. Let's say these three vectors, and you'll notice that I've drawn them so that the blue vector is really the sum of the red and the green vector, right? According to the triangle rule. So let's call the red vector u, the green vector v, then the blue vector is going to be u plus v. But these are the three sides of a triangle, or at least can be seen as such, right? And we know that in any triangle, any one side has a length which is no greater than the sum of the other two sides, right? So if we apply that to this situation, we can state that by saying that for any two vectors, the length of u plus v is less than or equal to the length of u plus the length of v. Okay? So this is again, this is a very traditional one. If you think about it, it's a very obvious kind of situation. It just follows from the fact that each side of a triangle has a length which is less than the sum of the lengths of the other two. But it is used theoretically in many places. We're not going to see many of them. We're going to stay away from the really deep technical subtleties of some of our proofs. But again, once again, I want you to keep this property in mind. Okay? So it's a classical result, useful mostly in theory, and we're not going to spend a lot more time on it.